Good morning, students. Welcome to another lesson for mathematics, secondary school mathematics. I'm your teacher, Mr. Ndenga Elphas, and today I will be discussing the topic linear motion. Linear motion is covered in Form 2, but if you look at what we want to discuss today, you'll find most of the things have been discussed in your primary school mathematics. And so I hope you'll find the lesson interesting and engage yourself, keep yourself busy with the calculators, and do the examples as we shall be doing them on our board. To start us off, let's first look at what is key in linear motion. And it's important to understand the meaning of the following terms. We have what we call distance. What is distance? Distance is a common word that we've been using all through. When we talk of distance, it simply means the length between 2 points. The length between two points. And when you're discussing length as a unit in linear motion, we need to understand that the SI unit of length, SI unit of this distance, that is meters. Meaning, in most of the calculation, we'll be finding the use of meters to be more applicable. However, we'll realize that we not only use meters, but we also go to the extent of using kilometers. So in most of the calculation under linear motion, we might use kilometers, yes, but the SI unit for distance is meters. Number two, okay, for example, if you are talking about these 2 points, this is the point A and B, the distance between these two, assuming this is 50 meters, then this is what you are calling the distance, if this length is 50. If I draw another point, let's say have a point Y, then AY, assuming it is 20 meters in length, then it means that is the distance. So distance is simply the length between 2 points, given in terms of meters. Number two, we will need to understand what we call displacement. We need to understand what is displacement. So students, what is displacement? When talking about displacement, we are talking about the distance. This is simply the distance covered. Distance covered by an object. By an object in a specified direction. In a specified direction. So there has to be a specific direction in which you are moving for you to say that that is displacement. If, for instance, your emphasis is to move from A to B, then we must be able to denote this not just as distance, but using an arrow to imply that we are strictly moving from A to B, for this to qualify as the displacement. If I'm moving from A, let's say to Y, then I have to indicate that it is in a specific direction to Y. And so it is not only just AY, which could be anywhere else, but it is from a specific point to a specific end point. So it has to be in a specific direction. And that is what brings in, when you're discussing distance, we now talk of what we call speed. We talk of speed. And speed is simply the total distance covered, we divide by the time taken, or rather what we call the average speed. You take the total distance covered over the time taken, meaning it's simply a ratio. Speed is therefore a ratio. Is a ratio of the distance, total distance to time taken. But then we give the units for speed in meters per second, that is the SI units. And some cases we are going to use kilometers per hour. Just because we've talked of distance being in kilometers, we will use kilometers per hour to represent speed. Close to speed, we need to understand there is also what we call velocity. And velocity is simply the speed in a specific direction. So when you are having speed in a specific direction, that is now what we call velocity. But when you have distance in a specific direction, we call it displacement. And therefore, it means, therefore, the concept for velocity comes from the displacement. And the concept for speed comes from distance. So those are the basic terms that we need to understand in the topic linear motion before we do the calculation. But just to review of what you learned in primary, if we review of what you learned in primary school mathematics, in terms of formulas, you are told that speed is distance over time, and you are told distance is speed times time, and time is simply the distance over speed. Those are the formulas that you mentioned in primary school, that this speed is distance over time, distance is speed times time, and time is distance over speed. These formulas will again be applicable in our case today. But because we have to do something different today, I want us to look at what is the most important area of this topic, and that is what we call relative speed. When we talk of relative speed, what do we mean? For example, you have two objects. You have two objects, and these two objects are moving in either the same direction at different speeds, or in the same direction at different speeds. But then these objects have either to cross each other or to overtake each other. If, for example, I am having a car, this is a car that is traveling from this point from point A to point B, at let's say X kilometers per hour. And we have another vehicle, this is now a Nissan that is moving, let's use a Matatu that is moving from B to A at Y kilometers per hour. Then these are two different speeds. But there has to be a point, if they are moving along the same path, there is a point where they will overtake each other, whether it is closer to A or closer to B, depending on which one moves faster. And so that is what we call relative speed. Simply the speed that is taken by the slow-moving object to overtake a fast-moving object at a given point. It can be in this case, so in this case, talk of relative speed being the sum of the speeds, x plus y kilometers per hour. And if they are moving the same direction, assuming now we have these two cases, we have this as A, B, and then I have the car which is at x kilometers per hour, and then this is the Matatu that is now moving at in the same direction, so meaning they are all moving from A. This is the Matatu, now going at y kilometers per hour. So if they are moving in the same direction, then we shall consider the relative speed as the difference in their speeds. So relative speed becomes either whether x is y minus x kilometers per hour, or x minus y kilometers per hour, depending which one is higher than the other. That is what we call relative speed. So we want to do questions that may perhaps require the application of those four things. Either we look at this speed is distance over time, distance is speed times time, and time is speed over distance over speed, or we shall have an application of relative speed. So those are the things I want us to discuss using the following questions. You are told Number one, a car travels, that is traveling at 60 kilometers per hour, left Nairobi for Eldoret at 7:30 a.m. 2 hours later, a bus left Eldoret, traveling at 90 kilometers per hour towards Nairobi. Given that the distance between Nairobi and Eldoret is 360 kilometers, calculate part A, the distance covered by the car before the bus left Eldoret. Number B, we calculate how far from Eldoret did the two vehicles meet. And number C, time of the day when the two vehicles met. That is a question that we want to discuss, and perhaps that will be 10 marks question to see how we apply all those 4 items we've listed before. And as you can see, it's a word question. And as always, when you are doing such a question in an exam, it's important that you first do the reading as you sketch where there is need, or you just take down important points in the question so that you use it now with relevance to the question in your calculation. So this is a car, and let's assume that this is where we have the location of Nairobi. This is Nairobi, and let's have this as the location for Eldoret. And so if these are the 2 points, then we are talking of a distance of 360 kilometers. Students, the car is leaving Nairobi at 7:30 a.m. So we indicate 7:30 a.m. and is traveling at 60 kilometers per hour. The direction is towards Eldoret. And 2 hours later, so it means at 9:30, that is when the bus leaves Eldoret, 9:30 a.m., traveling towards Nairobi, and it's going at a speed of 90 kilometers per hour. From the concept of relative speed that I've explained before, you'll be able to see that these speeds are different. And one of the reason why they are different is that if we are to look at where these two will meet, then the bus has to move a bit faster than the car, because the car left earlier than the bus. And that is what is asked in part A, that we determine the distance that the car had covered before the bus left Eldoret. And so what we go to is distance is speed times time. So the car had a time difference of 2 hours. And so we take 60 kilometers per hour times 2 hours to get 120 kilometers. So it means the car had moved 120 kilometers before the bus left Eldoret. So let's now say on our diagram that this is 120 kilometers. Let's say that is 120 kilometers. Then part B will then now require us to use the remaining distance. The remaining distance is 360 minus 120. So the remaining distance is actually 360 less 120, and that is 240 kilometers. So there's anything that will be discussed about the bus has to be mentioned within 240 kilometers so that we can be able to compare it with what the car is moving. And so I want us to assume or to let the two vehicles meet at point X. And so I will then come to my diagram. This is point X. So this is where they are meeting. Where we have the red line, this is the meeting point. And we say, let this be X kilometers. This distance will be X kilometers. So therefore, students, what is the distance from X to Eldoret? The distance from X to Eldoret will be 240 less X kilometers. That is the distance from X to Eldoret. The next thing will be, what must we let to be the same for these two vehicles to meet at X? Two objects are moving, or two vehicles are moving in the opposite direction or in the same direction. For you to ensure they meet at a common point, there has to be a unit that has to be the same. That is the unit that we want to discover here. And practically, the speed cannot be the same. And that's why you have 60 kilometers per hour with 90 kilometers per hour. So we rule out the speed is not the same. The distance, again, is not the same. We have X kilometers and 240 minus X, meaning distance is not common. So what are we left with? It's time. That time must be the same. So we'll say, for them to meet, for the two to meet, time must be the same. So that if the car takes, let's say, for example, 1 hour to move from this point to X, then the bus has also to make sure it takes 1 hour for them to meet at point X. And how do you get time? Time is distance over speed. So I will denote this as my time 1, T1, and my time 2, T2. So we'll say T1, which is now X, over the speed, 60, has to be equal to T2, which is 240, less X, over the speed, which is 90. So once we have this, we cross multiply. And for the sake of our question, we'll move to the far end. We have 90x is equal to 60 times 240. 60 times 240, that is 4 less 2, 12, 14, then you add 2 zeros, minus 60x. We collect like terms. I'll take negative 60 to the left side, so we have 150x is 14,400. Then we divide by 150, so that this cancel out. 5 is 3, 5 is 2, 44, that is 8, 40, that is 8. And 3 is 1, 3 is 9, 3 is 6. So x is 96 kilometers. So what that implies is that the car had moved 96 kilometers from this point to where they met with the bus. But the question is asking, how far from Eldoret did the two vehicles meet? So we now use the expression for 240 less x. So from Eldoret, the two met 240 less 96 kilometers. And this should be 10, that is 4, 3, that is 4, 144 kilometers from Eldoret. So we shall have our answer is 144 kilometers from Eldoret. Part C, the time of the day when the two vehicles met. The time of the day when the two vehicles met. We go back to our diagram and look at the expression for time. So the first expression for time is T1, which is x over 60. So I simply replace x with 96 and then divide to get time. So see, time is distance over speed, and our x is x over 60, implying 96 over 60. If we simplify this by 4, 4 is 15, and then 4 here is 1 into 30, that is 1 twice, sorry, into 16, 4. Then 3 is 5, 3 is 8. So this is 1 and 3 over 1 and 3 over 5. Now 1 and 3 over 5 hours. In terms of minutes, this is 1 hour, 36 minutes. That is 1 hour, 36 minutes. So what we only need to do is take 9:30, the time they met will be 9:30, we add 1 hour, 36 minutes, and if you add this, that is 11:06 a.m. 11:06 a.m. That is the time when the two vehicles met. And that is to mean that the bus had covered 1 hour 36 minutes for them to meet at the point X, which was 144 kilometers from Eldoret. I hope that is clear. That is for two objects that are moving in opposite direction. Let's try one where now the objects are moving in the same direction. And I hope you are able to see that the relative speed, because they are in the opposite direction, we have 60 plus 90, that's why we got 150 kilometers. We could have a case, let's say use this case as number 2, and say a car left town P at 10 a.m. traveling towards town Q at 40 kilometers per hour. So we can have let's say at 11:30 a.m. a motorist left town P, for Q at 60 kilometers per hour. at 60 kilometers per hour. Then you're told you calculate part A, the time when the motorist overtook the car. Then part B, the distance from Q where the motorist overtook the car, given that the distance between P and Q is 300 kilometers. A car left town P at 10 a.m. traveling towards town Q. At 11:30 a.m., a motorist then left town P for Q at 60 kilometers per hour. Then we calculate the time when the motorist overtook the car and the distance from Q where the motorist overtook the car, given that the distance between P and Q is 300 kilometers. Step by step, students, again, get the main concept from the question as you draw or you highlight them for easy calculation. So I would prefer that we sketch again, just as we did in question 1, and put it diagrammatically, having this as point town P and this is town Q. And in this question, it is about the car and the motorist. They are all moving in the same direction. But the good thing is that they all have different speeds and they start at different times. So we'll say if the car is going at 40 kilometers per hour and the motorist going at 60 kilometers per hour, the time for this case is 10 a.m. and this one is 11:30 a.m. So the first thing that we need to determine here is how far had the car gone by the time the motorist is leaving P. And that is captured in the time difference. And the time difference here is 1 hour 30 minutes, which is simply 11:30 with less 10 a.m. So 1 hour 30 minutes. So we calculate the distance that the car had traveled in 1 hour 30 minutes. So how do we get the distance? We've mentioned that distance is equal to speed times time. So for this car, we are going to say the speed is 40 and the time is 1.5 hours, so 3/2. If you simplify, you get this is 60 kilometers. So the car had covered 60 kilometers by the time the motorist is leaving P. So on my diagram, I will locate 60 again, 60 kilometers. And look at the concept as. The concept as is the car is being overtaken by the motorist. So for this to happen, then definitely the motorist has to be moving at a very high speed to be able to overtake the car, which has already covered 60 kilometers by the time the motorist is leaving town P. So what do? Let's let the motorist overtake the car at point X. So if I let this to happen and represent it on my diagram as X, I will definitely give this X kilometers, which is not known. So meaning that the motorist has to move 60 plus X kilometers, and the car has to move X kilometers at their respective speeds for them to be able to overtake each other at point X. Back to situation 1 in question 1, for this again to happen, practically looking at these two speeds, they are not the same. Looking at the distance to be covered by both the motorist and the car, they are not the same. So what remains to be the same has to be time. So in every case for linear motion, fight to ensure that time is the same. Whether your speed is high or is low, whether you're covering a very long distance or a very less distance, ensure always time is the same. So we have to make time to be the same in this case. So we'll say the time taken by the car, distance over speed. The distance will be X, and the speed for the car is 40. Time taken by the motorist. Again, distance over speed. The distance now will be 60 plus X over the speed, which is 60. If that is going to happen, then we will be very much sure that the motorist will manage to overtake the car at the point where this time is the same. So time being a constant factor here, X over 40 should be equal to 60 plus X over 60. We cross multiply, so we'll have 60X equal to 40 by 60, that is 2400, plus 40 by X is 40X. We collect like terms. That means we take 40 to the left side, it becomes minus. 60 minus 40 is 20X, is 2400. And if you look at this case, these two objects are moving in the same direction. And we said the relative speed is the difference between their speeds. And that is why 60 less 40 is 20. So let's get our X. Divide this by 20, divide this by 20. So we'll have this cancel, and X is, this is 120 kilometers. So it is 120 kilometers from where? From this point, so that we cover the X kilometers. Now, before we look at the question for the distance, we are supposed to look at the question as part A is to determine the time when the motorist overtook the car. So we go back to the expression for time. Time is distance over speed. And so we use our first expressions, X over 40, our X being 120 over 40. So this cancel out, and the answer is 3 hours. But this is simply time taken. So the exact time of the day, when the two overtook, now time the motorist overtook the car will be, we now take 11:30, we add 3 hours, and that gives us 14:30 hours in 24-hour clock system, or you can write it as 2:30 p.m. That is the time. That is how we work out the time for these two to be able to overtake each other. But then part B, we are told the distance from Q where the motorist overtook the car, given that the total distance is 300. That is very simple. If from P to Q is 300 and they are overtaking at 60 plus X, that means 120 plus 60 is 120 plus 60 is 180. So for part B, simply take 300 kilometers, we minus 180 kilometers. So that is now 120 kilometers from Q. Therefore, that is how we work out linear motion when we have either two cases. One case of an object which is moving in the same direction, and for the object which are moving in the opposite direction. Before we conclude our lesson, I want us to look at something again in linear motion. In linear motion, we talk about graphs. That is where we introduce you to graphs that then becomes very helpful in calculus in Form 4. And the graphs that we look at here are basically what we call the linear motion graphs. But for this lesson, I want us to discuss one graph because of time, and that graph is a graph of velocity time graph. I know we have what we call the distance time graph with the displacement time graph, which are always straight line graphs. The distance time graph, the displacement time graph, they are always straight line graphs from the origin. And so students should already have any problem with discussing of distance time graph and the displacement time graph. Because what we shall be doing in that case only get what we call the gradient of each of the graph to determine the next component quantity that will be asked. But now when discussing the velocity time graph, it is not a continuous straight line graph. So what happens in a velocity time graph, this is simply a graph of velocity y-axis against time on the x-axis. The velocity, remember, is in meters per second, and time is in seconds. So it then brings out this part where we say that the velocity time graph is not a continuous straight line graph. And that takes us to where we began. We said that velocity is simply speed in a specified direction. That as much as you're looking at how many kilometers you moved, it has to be in a specific direction. And that is why we go to the displacement. In obtaining the displacement, now we have the velocity time graph, which appears in this form. When you draw a velocity time graph, you'll find it takes this shape. On the y-axis, we are saying you have velocity in meters per second, and this side we have time in seconds. So what we have is the object moves from the origin, rising to a certain point. When it gets that maximum point, the object takes a different shape, that is straight line, the horizontal straight line. And then up to a certain point where now the object turns and moves to the x. So we can label this as point O, point P, point Q, and point R. So as students, you need to know what happens at each point. What is happening at point OP, point PQ, and point QR. We're talking about OP. The object or the particle is rising. So it's moving at an acceleration. So here we have acceleration. At this point PQ, when this is horizontal, then this is where we talk of constant velocity. And lastly, at the point QR, we talk of deceleration. So the object will either accelerate, move at a constant speed, or decelerate. We're talking about deceleration is simply the negative acceleration. This is negative acceleration. Negative acceleration. And so at some point you'll be asked to determine what we call the total distance covered. So in this case, the possible questions here will be either you'll be asked to determine acceleration, The examiner may ask you to determine acceleration, which you are saying it is this first point where the object is rising. Or the examiner will ask you to determine the constant speed, that's constant velocity, or time taken for the object to travel or to move at a constant speed. That is another area that the examiner might ask, what was the constant velocity, or how long did it take for the object to travel at a constant speed? And then lastly, they may ask you to determine the deceleration or the negative acceleration. Or you may be asked to account as to why this is negative. Those are the possible areas that we may be asked from this diagram, plus the fourth one, where you may be asked to determine total distance covered. And when you are asked to determine the total distance covered, what you need to do is calculate the area under this curve. This can form 3 or 4 objects or figures. Subdivide them and calculate the total area. That will give you the total distance covered. So this one simply get the area under the curve. So if you understand those areas, then you'll be able to work out questions on velocity time graph. And they are very good graph because such graphs prepares you for what you shall be doing in Form 4 some years to come in calculus. So let's look at one question on this, and then we conclude our lesson. You are told that the figure below shows a velocity time graph of a particle moving from point P to point R through point M and N. Through point M and N. So this is the graph. This is the graph with velocity, meters per second, with time in seconds. And so let's draw it this way. This way. So we put this as point P, and this is Q, M, and N. And ensure as you're drawing that this point is on the level of 40, and then this one here is on the level of 10. This one here is on the level of 40, and this one here is on the level of 50. That is where Q is. So that is the velocity time graph for this particle. And then you are asked determine part A, acceleration of the particle. Part B, time in seconds. Time in seconds when the particle was traveling at constant velocity. And part C, the total distance covered by the particle in meters. So those are the questions that you've been asked from that diagram. Since we have discussed the velocity time graph in detail and seen what we do, when you are given the figures, it should be easier for you. If you look at the diagram, the maximum velocity that this particle attains is 40 meters per second. And the highest time, or the maximum time taken to move from P to Q is 50 seconds. We've been told to determine the acceleration of the particle. How do you get the acceleration? We've discussed before, it is this along this path. And by now we know that acceleration is given by simply the change in velocity over the change in time. In simpler words, for those who've learned gradients and equation of straight line, we determine the gradient of this line. Putting in mind that the starting point is at O, point 0, then we'll say the maximum value on the y-axis, which is this velocity, is 40 less 0 over 10 less 0. That is 40 over 10, which is 4. And students know that the units for acceleration is meters per second squared. Meters per second squared. Now, if you find you've forgotten the units, you rather don't write the units, because when you write wrong units, you will not score the mark. So ensure you write the correct units for acceleration is meters per second squared. That is done for part A. Part B, the time in seconds when the particle was traveling at a constant velocity. So this is where we are describing the object moving at a constant velocity along that horizontal path. And the time taken is simply, at its maximum is 40 seconds, and at its minimum is 10 seconds, and so the difference is 30 seconds. That is the time that is traveled at a constant velocity. And part C, the total distance covered by the particle in meters. And we've discussed before, we said the total distance is simply given by the area under the curve. Area under the curve. So we have one curve, but we have three kinds of figures that we can obtain from here. We have this as the triangle, this as a rectangle, and this as a triangle. So we'll calculate area of 1. And let me label them to have this as 1, 2, and 3. Area of 1 is a rectangle, is a triangle, and the formula is a half base times height, which implies a half. Now what's the base? From O to 10, that is the base. 10 to the maximum point M, that is where you have the height. So it is 10 times the height of 40. This cancel out, this is 20, that gives us 200. Area 2, area of 2. Now which shape is 2? If you look at this length, from 10 to 40 is 30, and this is 40, then that tells you that is a rectangle. And area of a rectangle is length times width. So 30 times 40, that should give us 1200. And lastly, number 3 is again a triangle. So area of 3, a half times base times height. So a half times the base again. The difference between 50 and 40 is 10. That is times 10 times 40 to give us 200. And so therefore, what's the total distance covered? Total distance covered is equal to, we take 200, you add 1200, you add 200, and that gives you 1600 meters. That is the total distance covered by the particle. So that is how we look at those important areas in linear motion. We've discussed about the formulas for distance, speed, and time. Then we've discussed relative speed, and now velocity time graph. Next time, perhaps we'll be able to discuss the other graphs and see how we work them out. But for now, that is all for our lesson today. I wish you a nice day. Thank you.